My name is Margret. In this video, I help you get started with writing recursive methods using CodingBat. CodingBat is a project from Nick Palante from Stanford University. It includes literally hundreds of coding challenges, including dozens for recursion. Here you can see Recursion-1. It has 30 coding challenges. They start with factorial, they get incrementally harder, row by row, until you hit the last one, and then you're ready for the next level. He also has Recursion-2. But in order to ever get there, you have to get started. So let's have a look at factorial. By the way, you can create a free account. If you do so, you get green check marks every time you complete one of the challenges. Let's have a look at factorial. Given n of 1 or more, return the factorial of n, which is n times n minus 1 times n minus 2 all the way down to 1. Compute the result recursively without loops. And then it gives you some examples. Factorial of 1 is 1, factorial of 2 is 2 times 1 is 2, factorial of 3 is 3 times 2 times 1, that is 6, etc. Now notice, here you have the method body and the method header, but nothing returned yet. I can't really run the program yet because it doesn't compile. We promised it returns a value, we haven't done so. One thing I can do is I can say return 0 to do, and that makes it compile. Now 0 is not the right answer for the factorial, but it allows me to run it, and this way I can show you how CodingBat works. You can run your code and then you can get this immediate feedback whether it's right or whether you still need a little bit more troubleshooting. In this case, obviously it's not right, so we need to come up with a better plan. We're not allowed to use loops, we have to do it recursively. So what does it mean to solve a method recursively? There are two things that are very important. One is, if I want to write a recursive method factorial, that means I have to call this very method factorial in my implementation. That is important. The other thing is, I can't just keep calling it over and over again. I need to stop it eventually. I need an exit strategy. That is the base case. That means I need at least one situation where I know the answer, where I can compute it simply and easily without calling factorial. In order to think this through together, I prepared a couple of slides. Let's have a look at them. So here you can see the same expression that we saw on CodingBat before. N times n minus 1 times n minus 2 all the way down to 1. One thing I changed, I wrote n with an exclamation mark. That is a common way to write n factorial. Makes it a little bit easier on my slides. But at the end, I will bring back the method notation like factorial of n. So here, when I look at the examples, 3 factorial is 3 times 2 times 1 is 6. 2 factorial is 2 times 1 is 2. 1 factorial is 1. Here I have my base case that can be solved directly. Now I have the same equation again. This time I colored the n red because I would also like to look at the following question. What is n minus 1 factorial? I substitute each of those n with n minus 1 like this. And so here you can see how they line up. Each n has been substituted with n minus 1, but then of course I can simplify. N minus 1 minus 1, that would be n minus 2, or n minus 1 minus 2, that would be n minus 3, etc. So we can do that. Now I do one more thing. I'm going to add a couple spaces just to line up nicer, and you can see there is a lot of similarity between those two rows. One thing I also want to point out, if I look at this area here that is so similar, I can see a couple dots, and here I can see n minus 3 times a couple dots. Since those dots really mean keep multiplying with smaller and smaller numbers, successively smaller numbers, until you reach 1, doesn't really matter whether I add one more or less. So we can also include this n minus 3 in those dots, which means keep successively subtracting 1 until you reach eventually 1. And at this point you can see there are parts that are exactly the same in both of those equations. Not only that, you can also see that the part that is the same is n minus 1 factorial, because there is an equal sign right here. So because of this equal sign, I can substitute what I had in my first row, which was exactly the right side, with the left side, which is equal, which is n minus 1 factorial. Now that is an important step. It's an important step because now we have a reduction step. The reduction step takes us a step closer to the base case. First we had the challenge of figuring out n to factorial. Now I only have to figure out n minus 1 factorial. That's a little bit closer to 1, given that we are starting with positive numbers. Here I would like to look at an example. So let's just say my n is 4. In this case I might say 4 factorial is 4 times 3 factorial, which is all good, but now I have to figure out 3 factorial. 3 factorial is 3 times 2 factorial. Great, we can do that. 2 factorial is 2 times 1 factorial. And 1 factorial, we know that one. We talked about it. That is the base case. 1 factorial is 1. Now that we know that, we can bring up 1. That's the result of 1 factorial. If we say, well, 2 factorial, that is 2 times 1, that is 2. Great. Now we know 2 factorial is 2. So 3 factorial is 3 times 2, that is 6. Great. So now that we know that 3 factorial is 6, we can say 4 factorial is 4 times 6, that is 24. And at this point we know 4 factorial is 24. So we had to go all the way down, figuring out the factorial until we hit the base case, bring back the result to complete the expression and be able to produce the final value for 4 factorial, in our case 24. So let's bring back the method notation, factorial of n and factorial of n minus 1. So here you can also think of it this way. We're calling the method, we're passing 4 as the argument. Now we say, well, we have 4 times factorial of 3. So we could say we're returning 4 times factorial 3, calling the same method again, but this time with a different argument. Now, when I call this method with the different argument, you know, I can't really return it yet because we don't know this result. We have to figure that out first. When I call it with this different argument 3, I would want to return 3 times factorial 2, but I have to hold on. First, I have to figure out the factorial 2. So I'm calling it again, but this time I say, well, it's 2 times factorial. We're passing 1 as the argument, factorial of 1. Now, here we also need something where we say, well, hey, if n, the argument that we're passing to the method, happens to be 1, don't call factorial anymore. Return 1. That's the base case. So here we are returning 1. And because we return 1, now we can complete this expression. 2 times 1 is 2. Now we can complete the expression 3 times 2 is 6. Now we can complete the expression 4 times 6 is 24. And that is what factorial 4 is going to return. Now let's look how the code could look like. Here you can see we have a base case. If my n is 1, then return 1. Don't call factorial anymore. But otherwise, return n times factorial. Now importantly, we don't just call factorial with n again. We did this already. If we keep calling it with the same argument, we keep doing that forever. We don't get any closer to the base case. We need to call it with something else, with a different argument that takes us a step closer to reaching the base case. In our case, that is n minus 1 because we have positive numbers and we want to bring them down to 1. At this point, I'm going to take this code snippet and copy it into CodingBat. So here we are. I copied the code that we just figured out together here into the factorial. It still shows all the red feedback because we were running it with 0 before, but now I want to press the Go button and see what happens. And if we do so, you can see all of our tests turn green because now we provide the correct result.